welcome everyone and who's attending this event. My name is Paul. I'm an engineer at Private AI, working on model training, evaluation, model development, deployment sometimes, um, doing a lot of experiments as well. So my work at Private AI is about text redaction, fake integer generation. Prior to joining Private AI, I had 3 years of AI research experience at MILA and McGill, working on summarization, temporal knowledge graphs, and some spatial temporal prediction related to time series. So my presentation today will cover the privacy risks of language model as well as the ways to combat them, namely the differential privacy. So let me start by introducing the Private AI's PI redaction interface. Um, we have a text that contains many PI that is private information about individuals. It could be from a chat script or a call transcript. But then you want it to train your model. Because of the regulation, sometimes you would go through like manual, a lot of manual labor to produce the contents on the right. At Private AI, we do this automatically by using a named entity recognition model. So you could see that all these private informations are extracted and replaced with a type tag. The second service that I'm actively working on is fake integer generation. So you could tell that the kind of redacted text is not really useful for training, but they could be useful for like compliance. In order for it to be useful, you would need to generate some fake data that doesn't really lose the semantic of the context. Okay, so but why do we need redaction in the first place? Yeah, there is compliance, but I would like to dig into more of the technical risks in the large language models. So I will cover what are the privacy risks in the language models, what are the solutions, and why is a private AI solution unique. So large language models are the foundations to many NLP applications. The large models with the billions of parameters trained with the terabytes of data sets are pretty common these days. But with great power comes great risks. Have you wondered like what kind of information can be leaked by the language models behind this the commercial product? For example, Gmail's autocomplete model is trained on private communication among the users. And if the model leaks PI, it could break the contextual integrity, which is that private data should not be used outside of its intended context. And it turns out that language models can leak such information when facing a variety of attacks, and the lack of measure to protect the model privacy can result in serious data leakage and damage the image of the product and the company. Here's a meme about the like model leaking the text. Long live the revolution! Our next meeting will be at, and the model basically spits the rest. Actually, it could be a real attack in real life. So let's first look at the types of attacks on deep learning models. The first one is a membership inference attack, where so an adversary can predict whether or not a particular example was used to train a model, but he needs to come up with an example in the first place. And the second attack is more dangerous kind, where an adversary can reconstruct the training data points from the model output. That means you don't need to come up with the data point. You could just extract it, and as we will demonstrate later. The third kind of attack, which we will not cover, but is so prevalent, is called model extraction attack, where an adversary with only the query access to an ML model attempts to reconstruct a local copy. An example would be querying the Google Translate with like 10 million queries, and use those to train a English to French translation model, which could be pretty successful. And but it won't be covered in this talk. Okay, and inside, they could further be categorized into black box and white box attack. So in the black box attack, the attacker can only see the output of the model on arbitrary input, but can't access the model parameters. An example would be model ML as a service, for example, Google Translate, auto completion, etc. As shown here, and we will not cover is the white box attack, where an adversary can see additionally the weights and the intermediate representations of this process. So and in terms of defense, we will cover the differential privacy, which focuses on adding noise into the representation or gradient during training, and then a data sanitization, which identifies and redact the personal information in the training data. Notice that the PI's de-identification software belongs to the second category. Let's start with the membership inference attack. The first paper we'll cover is called ML leaks, which is an early paper that demonstrates the feasibility of membership inference attack under 3 assumptions: the white box, black box, and the data transferability, which is like basically 3 scenarios ranging from easy to hard mode. And they show that on all the three assumptions, the attacks are feasible. You could observe by this graph that adversary 1, 2, and 3 can both successfully perform this attack, while adversary 3 needs like more sophisticated attack, but they could achieve certain like level of accuracy, even under the white box scenario. So when the candidate space is small enough for the attacker to enumerate the membership inference attack would pose a threat to the data confidentiality. So there are other membership inference attacks that are applied to embeddings and text classifier, for example. And if you're interested, you can look at these papers. The second more dangerous and serious attack is called training data extraction. The attacker can extract the private information memorized by the model by crafting the attack queries. We will cover these 3 papers. 2 of them are actually by the same authors, and the final one is about clinical information. The first one is called the secret share, evaluating and testing the unintended memorization. They introduced this unintended memorization as a concept, where the model can memorize details about the training data that are unrelated to the intended task. When trained on the private data, it can reveal private information such as the user's names, credit card, and numbers. So here's an interesting attack. Let's add an example to the Pentric bank dataset. Nicolas' social security number is 281265017. We train a neural network on this augmented dataset, and then we query the model with the following prompts. So here the white text represents the prompts, and the red text represents the output by the model. When you only give the model a single hint, it doesn't really produce anything. And you give it a 2, it generates some random address. And we give it 2 numbers, 2, 8, it starts to generate something meaningful. And surprisingly, when you give it just 3 numbers, it produced the exact text that was inserted. So voila, with only the first 3 numbers in the prompts, the extraction attempt is successful, the attack could drastically reduce the attack space from 10 to the power of 9 to 10 to the power of 3, which is really dangerous. And actually, this is validated by a real experiment, which is really close, by inserting this canary that random number is, blah, blah, blah. Okay, so to summarize, to evaluate the unintended memorization, you need to generate a canary, insert the canary into the training data, train a model, and then compute the exposure. So how do you extract actually extract one? So by brute forcing, you just enumerate all the possible sequences, compute their perplexity, and find the ones with the lowest perplexity. So this can be done with, efficiently with shortest path search algorithm. The exposure metrics measures the relative difference in perplexity between the canaries and other random sequences. And here's the formal definition. It's basically so R here is the size of the random space of candidates, and then SR is the canary, and this metrics basically outputs the negative log rank of the canary, and it measures how likely the model will rank the canary above another random candidate, which means if it goes larger, it's more heavily memorized by the model. Here are some interesting charts. The exposure of a canary increases as the number of insertion increase. As you could tell, when the number of insertion is 4 or more, it is fully memorized by the model, which is defined as exposure larger than 30. And memorization is not due to overfitting, which is really important. It occurs very early during training as the test loss gets smaller. And what's more interesting is that it gets smaller once your model starts to overfit. And the third lesson is that the memorization persists across different types of models and different model sizes. You could tell from all these different architectures, GAU, LSTMC, and different hyperparameters, the exposure would persist. Let me use a laser point. Yeah, the exposure would be pretty large. The next lesson, the correlation between exposure and the individual success extractions are pretty high. So all extractions are, so when your extraction get to a point of 30, the extraction is always possible, but no extraction was possible below this number. And here's a real world kind of extraction from an unrun email dataset. And the canaries are the existing private information instead of made up ones. 3 of them are extracted in less than 1 hour, and all the canaries are heavily memorized. As you could tell, the exposures are all dangerously high, and 3 are extracted. So let's look at the next paper, extracting training data from large language models. This paper demonstrated that GPT-2 can memorize and leak individual training examples. They proposed a text extraction from a large language model's training data using only the black box query access. In this example, they basically query the GPT-2 model with the prefix is Strasbourg, and the GPT-2 spits out a whole piece of text which includes full names, physical addresses, email addresses, and phone number, and these are just redacted for the privacy reasons. The entire pipeline works like this. So you start by generating many examples from the GPT-2 when it's conditioned on different prefixes, and you sort the example using one of the 6 perplexity-based metrics that are proposed by the authors. And finally, you deduplicate the document. So among all these duplicated documents, you choose the top 100 in terms of the perplexity metrics. And you do an internet search or you confirm with the own OpenAI team whether it's truly in the data set or not. The sampling metrics, the sampling strategies and the metrics include the following. Top-end sampling from the empty prompt, using a temperature to increase the diversity, and using the diverse text from the web script. And the metrics are all based on perplexity. One of them is called zlib, which is the ratio of GPT-2 perplexity and the zlib entropy as computed by compressing the text. And for all these 18 configuration, there's like 100 top examples. Among all these 1,800 candidates, they extract around 600 uniquely memorized training examples. So you could tell that 46 of these examples actually contains individuals' name, and they do not include the names of famous politicians. And another 32 example contains some form of context information. It's either phone number or social media handle. And among these 16 are the context information for businesses, and other 16 contains private individuals' contact details. Note that because the GPT-2 is trained on public data, the leaked data from this attack is not so damaging, but it really definitely says something about the security of these models. So under the best attack configurations, 67% of the candidate samples are extracted from the training set. Yeah, this number. Let's then talk about defense. So with all these different attacks, how do we properly train the model or hide the training data so that the attacker can't gain the intended information? The results show that GPT-2 is vulnerable to the data extraction attacks, and duplicating documents helps mitigate but can't prevent all attacks. And the differential privacy training helps avoid the training extraction attack, but it doesn't result. It results in longer training times and degrades the utility, as we will go through later. The third paper is really about using BERT, precision on clinical notes, and investigate whether it reveals PHI. I will go through this picture. They design three kind of attack. The first one is prompting attack. We have a sentence: Mr. Layman showed symptoms of diabetes. You query a mask language model that are basically a BERT, and you have some like weights that fine tune on these set of EHRs. By prompting the model, you essentially are provided with a mask and let the model predict the probability of my Y being a diabetes. And by probing, you insert the diabetes into the sentence and let the model decide what's the probability of the sentence being true. And by generation, you just like the previous paper, you use a prompt and then let the BERT decode from this prompt with the Markov random field language generator. I won't go through these details. So it turns out that the first two attacks result in lower accuracy compared to a baseline, but the third attack has a significantly higher hit rate. Here's the result. In the first line, you notice that 84.7% of the sentences generated from the model contains a name, and 34% of the top 100 scores contains real patient name, and among this 12% of the generated sentence also contains the true condition of that patient. So this is kind of a applied attack on the medical data. So finally, let's go through the defense technologies. And we start with the differential privacy. The basics are as follows. So consider two databases X and Y. They only differ by a single record. Okay, let's say John and Tom. And a randomized algorithm M, which takes the database and outputs a number. Right. M, it's differentially private if the output mx and my are almost indistinguishable from each other, regardless of the choice of x and y. Here's the formal definition. Um, Note that here's a epsilon, uh, a very small number, so that the exponential of epsilon will be very close to 1, meaning that you couldn't really tell between x and y as two databases. A popular mechanism in differential privacy is called Laplacian mechanism, which is essentially fx plus eta, where this fx is a deterministic transformation on x, and eta is a sample from a Laplacian distribution. DP-SGD is full names Differential Privacy SGD, was originally designed for unstructured data, which incorporate the concept of DP into the SGD, which is so popular in training deep neural networks. And we can actually apply this to train machine learning models, particularly the language models, by applying the DP-SGD into the training process. So the DP-SGD alleviates the private risks in deep learning in general, with the sacrifice in the model performance. It's a variance of SGD that preserves differential privacy while optimizing the neural net. Here's the algorithmic description of differential private SGD. You could note that like most of the procedures are really similar to SGD, except these two steps. So G itself is a gradient calculated from the loss, and the gradient clipping is basically you divide this gradient by a real value that is dependent on C, and then you also add a noise term whose variance is determined by the C, where C is actually controlled by your privacy cost of epsilon and delta. So what I mean is by specifying a privacy cost, you could derive a C, which then you could use to apply to your gradient, which guarantees that the result of the training satisfies your privacy guarantees. I hope it's clear. So I will cover the basics to the state of the art, and as well as the practical lessons on improving privacy utility and the performance using DP. The first paper is an early attempt using MLP as a language model. They pre-train a non-private language model on a large public dataset, a brown dataset, and they fine-tune the model on the private dataset through the DP-SGD. They demonstrated that the pre-training step is crucial. And the second paper is learning and evaluating a differential private pre-trained model. They proposed a differential private word piece algorithm, and they vastly increased the batch size to 128K to achieve something reasonable with a high privacy guarantee. Of course, this like we would usually use 1 to 8K, 1 to 8 as the batch size. So this is definitely a lot of compute and GPU requirement. And they use a smaller variance, more training epochs and large batch size, which they find leads to a higher privacy guarantee and a F1 score, as illustrated by these three figures. So as you increase the sigma, you get lower epsilon and lower F1. And as you increase your batch size, you get a better better performance in general. And when you extend your epochs, you would also get a better F1 and epsilon. And this one shows the effect of batch size. And the third paper, large-scale differentially private BERT, they focus on the large-scale pre-training of BERT using DPSGD, and they define the gradient signal to noise ratio as the norms of the aggregate gradient divided by the norms of noise vector. They achieved a high accuracy by scaling up the batch size to millions and increasing the batch size over time, and finally using a large weight decay parameter. So here's the picture that shows that by increasing your batch size, you actually get a higher noise to signal to noise ratio, which is reflected in your mass language model accuracy by increasing the same amount in a batch size. And this figure shows that by increasing your batch size from 200K to about 1 million, which is represented by the orange curve, you could obtain the similar accuracy by using a like 1 million batch size in the first place, which is really hard to obtain. So these kind of research mostly produced by Google and DeepMind. So other lessons are that large weight decay leads to better results. So they suspect the layer normalization makes the layers output independent of the weights. And then DPS, Gaussian noise to the gradients, the norms of the weights are increased, which in turn shrinks the actual gradient and makes the training effective. And finally, a large weight decay helps alleviate this issue. Also, they found using JAX primitives with the XLA compiler and TPU training improves the efficiency. And another paper is about benchmarking the different differential privacy and federal learning. They find that so all models degrade as the privacy requirement increases. At this direction. But smaller networks like Albert and Disturbed degrades much more gracefully compared to large models like BERT and Roberta. Another paper, large language models can be strong differentially private learners. They show that the performance actually drops by applying DPSGD can be mitigated by the following ways: using a larger pre-trained models, and again, large batch size, large learning rate, and smaller clipping norms. And they also propose changing the fine-tuning objective with input as mask. For example, calculating the probability of mask being awesome or terrible with determining the sentiment. And finally, ghost clipping reduces the complexity of the computing per example gradient norm, which this allows the private training cost almost the same amount of the memory as the non-private training of the transformers. These are just illustrations of the previous points. As you increase your embedding size and by parameter size, you get a better depth accuracy. It applies to both BERT and GPT style models. And with a larger batch size and a larger learning rate, you get a better performance with a smaller clipping norm. And also leads to a better accuracy. So large batch size resulting in higher gradient signal to noise ratio, which linearly correlates to the model performance. Finally, by using ghost clipping, they reached almost the same memory efficiency as the non-private training. Another paper, differentially private fine-tuning of language models. They, instead of updating all the parameters during fine-tuning, they just explore using different tuning the different adapters, which is more parameter efficient. So here you would fix the model pre-trained on a corpus, and then you only tune a set of a set of parameters that's aimed at adapters. They propose three kind of different adapters, and they show that the first one actually works the best, which adds a low rank matrix Li times Ri to the pre-trained weight matrices. Here are the results. They could achieve similar performance to non-private training with only 1% of the training parameters. Of course, like this epsilon is a bit high, and they found that LoRa works the best. Finally, let's get to another paper. So previous paper all focused on applying the DPSGD to the training, but this paper explores the privatization of text embedding and sentence embedding. They apply something called DX privacy, a variance of DP to the BERT fine-tuning through text-to-text and the token embedding privatizations. And also they propose the privacy adaptive LLM pre-training. I will skip this. Their token embedding privatization involves adding a n to the embedding, which is x, and n here is just a noise term sample from Laplace distribution, as you probably remember from the first slide. And also they propose token swap privatization, which calculates the same noise embedding and performs the nearest neighbor search and get the token embedding that are closest to MX, and replace the original token with the closest token that you just found. And for the sentence representation privatization, they add noise to the output of the encoder instead of on the token level, and they use it for prediction. But you could see that as you increase the you decrease the noise level, you get like a better text, which on the contrary means if you increase the noise from, let's say, the original sentence, you get more and more tokens that are swapped by like totally irrelevant tokens, which would hurt the performance a lot. Yeah, I should really include the results here, but you could really find that at a very high privacy level, you're basically changing the sentence semantics. So let's go back and look at what our system does. We kind of do this first step, which is targeting what are the private information, and then what are their types, and then we replace this private information with the corresponding fake information, such that it's not a noise applied to all the tokens indifferently, but a much targeted approach that deals with a privacy issue in the data. And you don't need to apply the differential privacy with like 100K batch size to achieve a similar or even better level of performance. So that will conclude my my presentation.